You've probably heard a ton about hydrogen being the clean fuel of the future, right? It's everywhere in the universe, and when you use it for energy, the only thing that comes out is water. Sounds almost too good to be true. But there's a big question we've got to answer first. How do we actually take all that potential and use it? How do we turn this super simple element into the electricity that's going to power our cars, our homes, maybe even whole industries? Well, the answer is hiding inside a really incredible piece of technology.
And here it is. Meet the hero of our story. This is a proton exchange membrane fuel cell, or PEM for short. Think of it as a super clean, quiet, and amazingly efficient engine, but with no moving parts. And today, we're going to dig into the research that's making them better than ever.
All right, so let's pop the hood on this thing and see what's really going on inside what's essentially a microscopic power plant. On the surface, the idea is just beautifully simple. You've got hydrogen fuel going in one side and oxygen just from the air around us going in the other. What comes out? Electricity. That's it. Well, that and the only byproducts are pure water and some useful heat. No carbon, no pollution, zip. So how does that magic actually happen? It's all about this tiny three-step electrochemical dance. Okay, step 1. At a spot called the anode, a catalyst gets to work splitting hydrogen atoms into their two parts, positive protons and negative electrons. Step 2, and this is the really clever bit. A special membrane in the middle will only let the protons pass through. The electrons? Nope, they can't get through. They're forced to take the scenic route through an external circuit. And get this, that flow of electrons, that's the electricity we can use. Finally, step 3. On the other side, at the cathode, the protons, those electrons coming back from their journey, and oxygen from the air all meet up and combine to form, you guessed it, water.
And to make all this happen, every single component has a super specific job, almost like a team of specialists. You've got the polymer membrane, which is really the heart of the cell, acting as that strict bouncer for protons. Then there's the catalyst layer. It's the chemical matchmaker where all the action happens. The gas diffusion layer, or GDL, acts like the lungs, making sure gases can get in and water can get out. And finally, the bipolar plates are the skeleton of the whole thing, giving it structure and making sure everything flows where it needs to go. It's this tiny, perfectly organized factory.
But here's the thing. Trying to understand and perfect this tiny factory is really, really hard. I mean, you can't just shrink down and watch it work. So to figure out how to improve the design, scientists came up with an amazing tool, the digital twin. So in the past, if you wanted to simulate the crazy complex physics going on inside a fuel cell, you needed these massive supercomputers running these really complicated 3D models. They took forever to run and were insanely expensive. But the research we're diving into today, from Dr. Rehab Jarala's dissertation, is all about a much more efficient 2D model, a digital twin. And the difference is huge. This new model runs on a normal computer, it gives you answers way faster, and it slashes the cost. This is a total game changer for R&D.
And here's why that matters so much. When you have a tool this fast and efficient, scientists can suddenly test hundreds of different ideas, new materials, different temperatures, you name it, to find that perfect recipe for the best possible performance. And they can do it all without having to build a new physical fuel cell every single time. It just puts innovation into hyperdrive.
But what are they actually trying to figure out? What's the puzzle they're trying to solve? Well, it turns out that getting the best performance out of a fuel cell isn't about just one thing. It's this incredibly delicate balancing act. So the real question is, what are those secret levers, the knobs and dials that engineers can tweak to solve this puzzle and squeeze every last drop of power out of one of these things? Well, one of the biggest challenges is something researchers call the Goldilocks problem, and it's all about managing water. Remember that special membrane? If it gets too dry, the protons just stop flowing. Boom, the whole process grinds to a halt. But if there's too much water, the electrodes can actually flood, and that blocks the oxygen from getting in. So it can't be too wet, it can't be too dry. It has to be just right. So, using that super powerful digital twin, what secrets did this research uncover? Let's get into the key findings that could really unlock that next level of fuel cell performance.
Okay, finding number 1. Full hydration is everything. I mean, look at this chart. It's a crystal clear comparison of the cell's performance with low humidity gases versus high humidity gases. The takeaway is simple. To help solve that Goldilocks water problem and keep the membrane happy, you have to make sure the gases are fully humidified before they even get into the cell.
Next up, finding number 2 is all about the environment you create for the cell.
The model basically asked, hey, what happens if we crank up the pressure and the temperature? And as you can see right here, the answer was pretty clear. Running the cell at higher pressures and higher temperatures gives you a serious boost in performance. It just makes the whole chemical reaction happen faster and more efficiently. And the third big find gets right down to the building blocks, the materials themselves. Remember that gas diffusion layer, the lungs of the cell? Well, the model proved that making this layer more porous, which just means giving it more open space, more little holes, lets things like oxygen get to the catalyst way more easily. And the same thing goes for the catalyst layer too. The bottom line? Better breathing means better performance.
What's so powerful here is that when you take all these findings and put them together, all discovered so quickly thanks to this digital model, you basically get a clear blueprint, a roadmap for designing the fuel cells of tomorrow.
And hey, don't just take my word for it. Dr. Girala's dissertation sums it up perfectly. It says that these models can serve as a useful tool for optimization of cell design and operating conditions. See, it's not just about understanding how they work anymore. It's about having a real tool to make them work better, faster, and cheaper.
And this really brings us to the final, most exciting thought. With incredible digital tools like this one speeding up innovation, we're not just making tiny tweaks to old designs anymore. We're creating brand new ones at a pace we've never seen before. So the real question is, what will this next generation of ultra-efficient, low-cost fuel cells make possible for all of us in a clean energy future?